Welcome back to another interesting section in your preparation towards your examination. I trust you are all geared towards excellence in this forthcoming examination. This morning, in our focus with respect to physics, which we'll be doing, we'll be looking at question series which you can actually find on the website. At your own convenient time, you can always check our platform, your study path website, for these questions. Now, getting straight up, we want to see as much as questions flowing from the line of calculations as well as non-calculation, such that we create a balance between all that we have learned so far. Let's get right into business. So, for the first question today, if you're told this, so imagine a question this way. A carpenter on top of a roof 20 meters high dropped a hammer of mass 1.5 kg and it fell freely to the ground. The kinetic energy of the hammer just before hitting the ground is going to be what? This portrays a question in relation to work energy and power. And having said this before, we said energy can neither be created nor destroyed. It can only be transferred from one form to another. This is actually a phenomenon whereby potential energy is being converted to kinetic energy. Potential energy at the top of the roof is being converted to kinetic energy. As such, having known the formula for potential energy as being mgh, we can relate it to the kinetic energy part. And based on the question presented to us, you can see that mass given to us from the question is 1.5, acceleration due to gravity being a constant, 10, and the given height portrayed, 20. When you get to multiply this, you have the kinetic energy. And from here, this presents us 300 being equal to the kinetic energy. It means the kinetic energy is equal to 300 joules. The kinetic energy is equal to 300 joules. That's simple. We are having energy conversion such that potential energy is converted to kinetic energy. And note, they were careful to say we should determine the kinetic energy just before hitting the ground, knowing fully well that when it hits the ground, then you are not going to have kinetic energy again. Then you are going to now have a potential energy form being returned back. So just before hitting the ground, the body, the hammer still possesses velocity. It still has velocity to itself with which it is moving. So there you have it, the answer to the first question. I'm sure it was quite easy to pull off. Let's quickly look at the second question. So here they're talking about two bodies of different masses being thrown up vertically upward. And here, in consideration to what happens to their masses, we are asked what would be their position having thrown the bodies up 1 minute later after being thrown up. Look at option A. We are told that X and Y will both be 500 meters from the point of throw B, we are told that X and Y will both be 500 meters from each other C, Y will be 500 meters ahead of X, and D, X will be 500 meters ahead of Y. So I'll leave you to that to look at in the space of 20 seconds thereabouts to come up with an answer. So I'll allow you to look at the answer and come up with what the answer would be. Just think about it. Just think about it. What would be their position after 1 second? Yes, tick-tock. Tick-tock, tick-tock. Okay, I'm sure you should have come up with your own conclusion. Here is the catch. For a body moving vertically upward, it's expected for us to understand that here we take into account Newton's equation of motion. If you are going to determine what the position is going to be after 1 second, then you'll be making reference to Newton's equation of motion and never Newton's laws of motion. Because we said that Newton's equation of motion will explain the kinematic aspect of physics for you, while Newton's laws of motion will explain the dynamics to it, meaning we take into consideration the force causing the motion. So as such, if you're having mass mentioned here now, the mass is not going to have any effect in the consequence of using the equations of motion. Among the 4 equations of motion, general 4 equations of motion, and among the 3 equations of motion dealing with vertical motion, none of them have a place for the mass to that effect. Mass would never play any significant role. Mass would not play any significant role with respect to this. And check what happens here. We want to determine the distance. We have various equations which we can use. The first one, V equals to U plus or minus GT, plus for a body coming down, minus for a body moving up. We have S equal to UT plus or minus half GT square. And the last one, V square being equal to U square minus 2GS plus or minus. Of these 3 here, being given the time value 1 second later, it means the t value is given. Also, being given the initial velocity with which the bodies are thrown up, we have that this would fit in as the perfect formula. And we are using S equals to ut minus half gt square. Check this out. We have S value to be determined. U value is 100 multiplied by 1 minus half multiplied by 10 multiplied by 1 square. From here, S becomes 100 minus, we have 5 from here. S is equal to 95 meters. You're going to have that both of them are going to attain a distance of 95 meters at the end of 1 minute, 1 second rather. So none of these options are actually correct. There's no way you have one being 500 meters ahead of the other, or both of them attaining 500 meters from the starting position, or both would be 500 meters from each other, or any of the option. No option is actually correct, because even in terms of the distance covered, we have that the distance covered is going to be 95 meters. So I'm sure that tallies with what you have in your mind. If not, I'm sure you now have a clear understanding to what the explanation is all about. Here, they are trying to be sure you understand the difference between using equations of motion to answer a physics problem and using the Newton's laws of motion to answer questions. Once it has to do with vertical motion, a body that is thrown vertically upward, we are making reference to equation of motion in the vertical direction. And these are the 3 formulas that would function. Out of the 3, we are picking this based on the parameters given. And the distance you are going to have is 95 meters, not any of the 500 meters portrayed here. I'm sure you got that. Let's look at the next question. Remember, give it your best shot. The questions, if you see them, try to understand which principle, which laws of physics applies to this particular question, and you find it that easy. So, we'll look at the next one quickly. Question 3. Also, a non-calculation question. Question 3, a non-calculation question. We are told that a man standing on a lift. A man standing on a lift that is descending. A man standing on a lift that is descending does not feel any weight because what would be the reason why a man standing on a lift that is actually descending would not feel any weight? A, we are told that perhaps because there is no gravitational pull on the man in the lift. B, the inside of the lift is airtight. C, the lift is in vacuum. And the last option, there is no reaction from the floor of the lift. So I'll leave you to that. Try to actually look at the question and try pick your own correct answer. Then we'll look at the corrections together. TikTok. Why would a man feel a sense of weightlessness when a lift is descending? 20 seconds to peak. Okay. Tick tock. Tick tock. Tick tock. Tick tock. Tick tock. Tick tock. Okay. What's your answer? Number 4. D. Okay, beautiful. Nice pull to that. Number 3, I suppose you wanted to write. Number 3 question. Interesting. Of all the answers portrayed here, the correct answer is going to be D. The correct answer is going to be D. And why is this? Check this out. A says there is no gravitational pull on the man in the lift. That's not true. We know we are not living, the man is not actually being in space where gravity is minimal. Here we have, there's going to be a gravitational pull on the man. Acceleration due to gravity will always act on anything coming downwards, moving downwards. So this cannot be the answer. The inside of the lift is airtight. Then you ask yourself, how is the man breathing if the inside of the lift is airtight? So that is not going to be something to consider. The inside of the lift is not airtight, meaning the air inside there is actually what? Is closed up. Then it means that it's going to use up the amount of oxygen present in the lift after some time. What has a lift being airtight got to do with the deceleration process of the lift? Nope. The next one, the lift is in vacuum. Then if there's no air inside the lift, then the man certainly would not survive. So all these don't play a key role as to what the question is talking about. This question is talking about the motion of a lift with respect to dynamics, as the case is. Here we go. You are expecting to have tension, which is the reactional force. You're expected to have reaction from the floor and upward reactive force for the weight of the man and the lift. You are meant to have that. But because the lift is moving downwards, you are going to have a downward acceleration A. There's bound to be a downward acceleration A. Acceleration is going to be downwards. And the reason is because you have the body moving, the lift moving what? Downwards. This is the catch. Since you're having the man feeling weightlessness, it means that you are having the acceleration of the lift being equal to acceleration due to gravity. That is one key thing. Check this out. We have that the weight must be greater than the tension, the upward reactive force, for you to have a downward acceleration. We have W to be equal to mg minus the tension, which is the upward reaction. Remember, Newton's third law says to every action you would always have an equal and opposite reaction. So that is the T you are saying here now, which is the reaction that is meant to act to balance up. So we have that this guy is MA. Now, when we have this guy coming here, this guy coming here, you are going to have that mg here can only be equal to MA when T is equal to 0. You can only have the value here being equal such that what? This guy, better put, you tend to see that when we collect like terms, bringing MA here, you have MA here, and the tension moves out away to the other side. From here, m into bracket g minus a would be equal to tension, where the acceleration of the lift becomes equal, almost equal to acceleration due to gravity. Then you have that m becomes g minus g, and that's t. Here we go, m0 equals to t, t is equal to 0. That's the condition whereby you have weightlessness. So it means that no reaction from the floor, there's actually no reaction from the floor of the lift. That's why you are experiencing a sense of weightlessness. The acceleration due to gravity is almost equal to the value of the downward acceleration of the lift itself. So this is synonymous to saying you're having a free fall situation. So the tension, which is the upward reactive force, is 0 in this case. Hence, no reaction from the floor of the lift becomes the correct answer. Let's take a look at the next one. I'm sure out of the 3 questions answered so far, you've been able to bag 1 in the box, or perhaps 2, or perhaps the 3. Let's check out this next one. Quite interesting a question, I must say. This one talks about 2 vectors. The first in this direction and the second in this direction. 8.0 Newton, 6.0 Newton. We're asked to find the resultant vector. What is going to be the resultant vector R? So among the formulas we have, what is going to be the resultant vector? You have to find the resultant vector. What's going to be the resultant vector for this part? Let's get to see it. The resultant vector. What's going to be the resultant? So this is a calculation question. Resultant vector. This falls among the special sides of a right angle triangle, such that we would always make reference to the special values. You can always determine what's the hypotenuse. The resultant vector is actually the hypotenuse of the given question, such that you use your formula, Pythagoras theorem, to actually derive your answer. So here we go. We know that having 6 Newton on this side, having 8 Newton on this side, the resultant is always the R value, the hypotenuse. I can replicate the 6 Newton here such that we have a right angle triangle. So, and we can easily say hypotenuse square is equal to the opposite square plus the adjacent square. So R square becomes 6 square plus 8 square. R square becomes 36 plus 64. Dealing with R square being 100, R value becomes 10 Newton. The R value becomes 10 Newton. That's quite easy to solve. Even without calculation, you know special values. When you have 3 and 4, you have 5 as the hypotenuse. When you have 6 and 8, you have 10 as the hypotenuse. And when you have 5